The webinar. My name is Subramaniam Rajan, and as you can see with the title of the presentation, today I'm going to be talking about teaching object-oriented numerical analysis. Let me tell you a little bit of myself before I get into the presentation. I'm a faculty in the School of Sustainable Engineering and the Built Environment at Arizona State University. Our schools of engineering is divided into 6 schools, and one of the schools, as you can see here, is called School of Sustainable Engineering and the Built Environment. We have 3 degree programs in the school: civil engineering, construction engineering, and construction management. I'm a faculty primarily in the Department of Civil Engineering. It used to be Department of Civil Engineering, but it's a civil engineering program. I'm also teaching courses at the graduate level in mechanical and aerospace engineering. So today's presentation I made at the conference in Pune, and I'm going to change that presentation a little bit to suit today's audience so that at the end we can have a more meaningful discussion. So my presentation will be for about 20-25 minutes. I'll give you an overview of what is done in the course that I teach. Then I'll show you a few other things like Visual Studio that's used primarily in the course to understand programming. Then I'll show you a specific project that the students work on towards the end of the course. And I'll also show you the Blackboard website that is used in interacting with the students. There are no handouts in the classroom. Everything is done electronically. So with that background, let's start looking at what this course is all about. So let me give you a motivation for teaching a course on object-oriented numerical analysis. Obviously, the audience that I'm looking at are primarily engineering instructors, engineering professors who are teaching courses in different engineering disciplines. At the end of the 4-year program, you expect your students to go and work in the industry, and almost always the engineering job will involve using one or more computer software. Now, while students may not be writing computer software for a living, they almost always will be using computer software. And it makes sense that the students know exactly how computer softwares are designed with the user in mind and what really takes place behind the scenes. Looking at computer software as a black box really doesn't tell the student what to expect when they go out in the industry and what exactly can these tools be used for. So in this slide, I'm showing you what engineering analysis and design is all about. There are 4 bullets here. Almost always, engineering analysis and design works with an approximate numerical solution. Very rarely do we have practical problems for which the exact answer is known. Since the exact answer is not known, there are a lot of numerical techniques that are available that generate various types of approximate solutions. And as a design engineer, one must know what these approximations are and when to use tool A versus tool B if these 2 tools use different type of approximations. The second thing to note is in all these engineering analysis and design, whether you're designing aircrafts or you're designing automobiles or you're designing buildings or you're designing electrical circuits, you have to manipulate a large amount of data. And this large amount of data can be of a variety of forms. Some of the data can be integers, some of the data can be floating point values that are single precision, double precision. Some of it is text data. Some of it is data that needs to be shown to the user in a visual form. Some of the data lend themselves to data mining so that the user can query the database and find out information. The third point to note is almost always, just like we have an approximate solution, we also don't have a unique solution. And you see examples of this every single day. For example, if you look at the automobile market, there is no set way of designing a particular vehicle. There are lots of different flavors in designing vehicles catering to different market segments. And the way you arrive at your solution obviously is not unique. There are lots of different ways of arriving at a solution or the same solution using different paths. And finally, when you're dealing with engineering analysis and design, a lot of computations take place. This is one of the biggest differences between what people do in the accounting business, where you deal with vast amount of data that is somewhat easier to handle because the calculations are not compute intensive. So engineering calculations are very compute intensive. They require extended precision. I'll show you examples today where most of the calculations are done using double precision arithmetic, because if you don't, then the answers are not going to be very accurate. And finally, as you've probably observed in the last 10-15 years, all the chip manufacturers, starting with Intel and AMD, are not making faster chips because of a lot of problems dealing with electrical leakage and handling the huge thermal issues that arise with faster clock speeds. So single CPUs that operate at a greater frequency and a greater throughput, that has declined. And what has increased in that scenario are newer chips where there are a lot more cores that lend themselves to parallel processing. And that remains one of the very big challenges in engineering analysis and design, is the challenges needed to take algorithms that have been designed for sequential execution and making them run in parallel. So numerical analysis, which gives us answers to lots of engineering problems, can be readily tied to computer programming. And here I've given you a 100,000 feet view of how the marriage takes place between numerical analysis and computer programming through a 4-step process. We typically start with a theory or heuristics. The theory or heuristics being developed to solve a specific problem, and the theory then is transformed into a detailed algorithm. And the detailed algorithm obviously is going to have several steps. And these steps then must be transformed into one or more computer programs in a high-level computer language. And this computer language must go through 2 steps after the coding is done. One is testing to make, and the second part of that process is, once the testing is done, is to deploy it and make it available to the end users. So this, when you start teaching development of computer programs at a higher level, you'll find that most of the students are not aware of what really takes place in a software company. What operations are necessary to take the end view of the product and translate that into concrete steps that then gets implemented in the form of a computer code. So the way I explain to them is to look at 2 key objects. One is the amount of time and effort and money that's going to take an idea and transform that into a viable computer program that's going to be sold and used by the end user. And then the challenges in making sure that the operation that you have done, that means the first sales that you make, is something that is sustainable into the future. That means the code can be maintained, the code can be enhanced, the code can adapt to the changes in the end user needs, and is agile enough so that the software development company is a viable entity down the road. So I look at 2 topics. One is the concept of using object-oriented approach in software development, and then the selection of an appropriate language. Selling the first idea, object-oriented approach, is a little more difficult because most of the concepts associated with object-oriented programming are abstract to begin with till you show concrete examples in the classroom in the form of case studies, and then case studies that evolve into homework and projects that the students must do on their own. If you follow that process, I feel it makes it easier to sell the idea of object-oriented programming, and then you can start selling an appropriate language that can be used. So for most of the software development that is done in the engineering arena is uses C++. There are obviously other languages that are available, including some higher level scripting languages. But the case studies that I'm going to be looking at and the course that I teach requires traits that lend themselves very nicely to C++. And the reason why I chose C++, and I've been using it for the last 2 decades or so, ever since the mid-1990s, is because C++ is a higher level language that has a very strong ISO standards committee that lays down the standards that all C++ compiler developers must follow. The language is used by millions of people to do a variety of writing a variety of programs, not just engineering programs. There is a rich set of libraries that are available for use and reuse, so that you don't have to start reinventing the wheel, and you can spend more time trying to solve the problems that you want the solutions to. So without getting into too many discussions on why C++, why not Java, why not a scripting language, which is something that really needs to take place when the students are more mature and have looked at more than one language. I start with the premise that C++ is the appropriate language to be used in understanding numerical analysis or tying numerical analysis to object-oriented programming. And then as we go through the course, show them why C++ is probably an appropriate language to use. So the course that I teach is primarily a graduate course, though there are senior level, that means 4th year students who are taking this course because they are more curious to know what is going to be covered in a graduate degree program and why computer program is an important part of most of the engineering degree programs. So the course is called Developing Software for Engineering Applications. There are 2 focus in this course because after half the course, the students split off into 2 parts. There is one part of the course which deals with geometric modeling, which is primarily taken by students from mechanical and aerospace engineering. And then there is another part which looks at solution to partial differential equations, which is primarily taken by civil engineering student. So the first half of the course discusses object-oriented programming using C++, and in the second half, which I'm going to focus on, is not going to be on geometric modeling, but will be solution to partial differential equations, specifically introduction to finite element analysis. Now, this is a rather unique course in the engineering curriculum and makes the task of assessment a lot more difficult, a lot more challenging. So the assessment bullet that you see in this slide is essentially in 2 parts. I do not give homework. I discuss lots of small problems to solve in the beginning of the course. And then we have in-class quizzes. So we spend the entire class, which is typically 1 hour and 15 minutes, where we discuss some of the parts of the questions which would be in the in-class quiz, in the lectures leading to the quiz. And then the quiz, I give them the problem statement that is slightly modified. They start with an existing program, which they have to then modify and which they submit at the end of the quiz. The second type of assessment that is done is in the form of 3 to 4 programming projects, and I'll show you one of the or a couple of examples that the students work through. The programming projects start with something very simple, like building a matrix toolbox, and then they gradually evolve into more complicated projects like writing a finite element analysis program for a space stress project, for a space stress analysis, or a planar frame analysis, or doing something that is graphical user interface where they have to manipulate a space stress, do simple operations like rotation, zooming in, zooming out, and so on. So the first major project that they see in the course is all these toolboxes that they need to develop. And typically these toolboxes are in the form of templates so that they are more readily usable and reusable in different projects that the students are going to be working on. So we start with STL, STL being a part of the C++ library, including handling strings, sorting, and all those other type of operations and data structures. On top of this, we build a matrix toolbox that relies on two important classes here. One is a C vector class designed specifically for high-level computations involving floats and doubles, and then a C matrix class, again, specifically designed to do matrix type of operations. So all the vector and matrix operations that you would typically see in an engineering computer program are used in the development of a matrix toolbox. And I'll show you the specific toolbox project that they are given, where they are asked to develop very simple functions like dot product, cross product, matrix addition, matrix subtraction, matrix multiplication, solving AX equals B, and so on. Then they also look at a couple of other toolboxes that they develop. One is numerical integration and differentiation, and then a token parser, where they have to parse an input file, a text file, find out exactly what is in each line of the input, parse the data, store it so that then it can be used in the applications that they're going to be working on. And the application that they're going to be working on, which I'm going to show you, will be a finite element analysis program. So what you can see here is if the students have never done programming before, this is not the course for them. I expect that the students have been exposed to numerical analysis and some programming in the undergraduate program. And at Arizona State University, in the undergraduate program, there is a course on numerical analysis, and then there is a course on using MATLAB as a programming language, not MATLAB as a black box. And they use MATLAB to write code to do a variety of things, including writing a very rudimentary finite element analysis program. So with that background, I build on teaching them object-oriented programming approaches, and then they start building all these toolboxes. Some of these toolboxes are given to them, other toolboxes they start developing from scratch. So the case studies and the final 3 or 4 projects that they need to do are a lot more complicated than what they have been used to. And I show them exactly how software development companies who do this for a living handle new projects and new program development. And you can see here the flow diagram that is shown here. This is called the waterfall flow diagram in computer science language. So you can see that it starts by looking at what the problem statement is, dissecting the problem statement, understanding exactly what the end user is looking for in terms of the program capabilities, then taking the problem statement and sketching out what the solution architecture needs to be. And I draw parallels between this and parallel between what takes place in a civil engineering A and E industry, architecture and engineering industry, where the end user may come up with the plans for a building. The architecture draws the plans for the building, turns it over to a structural engineer, that the structural engineer then converts into beams and columns, concrete and steel, and works with other engineering discipline people like geotechnical engineers, electrical engineers, mechanical HVAC engineers, and coming up with a final product. So I tell them the way the software development takes place is very, very similar, that there is a software architect in every company who draws the plans for the overall solution architecture, and then the solution architecture is then broken down into classes, and the class implementation then takes place in terms of modules. And then once the modules are developed in parallel, they are tested in parallel using testing techniques, unit testing techniques. And then finally, at some stage, you take all these modules together and integrate them into a system, and then you start testing the entire system. Now, when you teach a course like this, you have two options. Either you can have all these projects being done individually by each student, and this is what I do most of the time. 3 out of the 4 projects are done individually. I feel that's a very good starting point, because you really cannot work as a team till you have enough background, enough confidence in the way you tackle problems, in the way you debug, and you do module development and testing before you can work as a member of a team. And there is only one project at the end where I give the students the option of working in teams of 2. And then they understand exactly what the team dynamics plays in terms of software development. So with that background, I'm going to start looking at some sample projects that are given the course. And I'm going to break my presentation and start looking at Microsoft Visual Studio. And I'm going to show you examples of Microsoft Visual Studio, the way it is used in the course. So now you can see Microsoft Visual Studio being used. The nice thing about Microsoft Visual Studio is Arizona State University has a site license, and the entire faculty and the students can download a variety of Microsoft products for free. So this is of no cost to the student. It works very well on a laptop. Students bring the laptop to class every single day, so we really don't have to use a computer lab anymore. Computer labs were used maybe 10, 15 years ago, but today most of the students have very decent powered laptops that can be used inside the classroom in terms of using a very rich GUI interface system for software development. So here you can see the first major project that they work on, where they develop a matrix toolbox on top of the C vector and the C matrix classes. So here in the bottom of the screen, you can see the C vector template class. Very, very simple. They don't have to understand pointers to see exactly how it is implemented, though I do teach them pointers and tell them exactly how pointers are used and how pointers can be misused if not used correctly. And then they understand very simple things like what's an operator overloading, how can operator overloading make the code easier to read. And then later on in the course, I tell them if they really want to make the C vector class and the C matrix class really rich and want to make their C vector class and C matrix class behave similar to what they would see in a higher level language like MATLAB, what they need to do. And you can see here, I go through this entire code and I explain to them what is the function of each of these functions in the template library and how they can understand how the matrix class works and how the error handler within the matrix class can be used to detect very commonly found errors when you use vectors, when you use arrays, vectors and matrices. For example, memory allocation or row or column index being out of bounds, or the constructor being used incorrectly, and so on. Same thing with a matrix class, which has 2 indices, the row and the column number for the matrix. Again, template class that they really understand how to use. And then the matrix toolbox that is in the form of a template again, so that it can be used either with float or double or int, depending upon what matrix toolbox they're going to be using it with. And I'm going to show you an example of one function in this toolbox, which is solving AX equals B. So here is the function declaration, and here is the function spelled out entirely in terms of A, X, and B, and the tolerance in detecting whether the matrix is singular or not. This refers to the Gaussian elimination technique. So we discuss the numerical algorithm in the class. We look at different steps in the algorithm, and I teach them how the code needs to be documented so that you can look at the theory and look at the code and know exactly how the theory translates into the code. So every single step is marked here. They do operations count so that they know how many addition, subtraction, multiplication, division takes place in a function like solving AX equals B. And then unit testing through the main program. They create a single precision object and a double precision object for the toolbox. Then they start writing code to do different type of operations that are supported in the toolbox, to do various vector and matrix operations, how they can write a code that can automatically detect if the answers are correct or incorrect, and how they can do essentially unit testing. So this is their first exposure to doing something meaningful, something that can then be reused in the follow-on projects. So the next project that I'm going to be showing you is a finite element project, very simple. It's a program that does the analysis of a space truss subjected to a variety of loading like mechanical loads, thermal loads, and so on. So here is the main program for the space truss project. And again, we use very high level concepts like composition, inheritance. I show them when it can be used and when it can be misused, how code can be readily modified when they have to enhance the capabilities. For example, if you want to modify this truss program and add capabilities to include other finite elements, what changes do you have to make to the entire program, and how you can make sure that the changes are minimal in nature so that the code can be used very efficiently and the program capabilities can be extended very efficiently. The one thing that I really like to stress and I like in Visual Studio is the ability to use the interactive debugger. The interactive debugger is something that I teach them right from the time they have launched and run their first simple program. And I tell them exactly how the debugger can be used to step through the program one statement at a time, examine the values of different variables, see whether the variables look okay or not, find logical errors in the program, make corrections, launch the debugger again, and go through essentially a process of debugging, making corrections, doing the unit testing all in one loop. So after this, I'm going to go back to my presentation, and I'm going to conclude with my final slide, couple of slides here. So teaching a course like this, at the end of the course, you'll find that the students are very happy to have learned something by which they know that they have accomplished something very useful, something that's going to last them not only in the rest of their undergraduate or their graduate program, but these concepts carry over to the industry where they may or may not be doing software development for a living, but definitely they'll be using software, and they may be in a position of evaluating different software to see which one suits their needs. So a course or two on object-oriented numerical analysis-based software, I feel, is a must for all engineering students. Without this, it is going to be very difficult to understand how software is developed and how software needs to be used in the engineering industry. and how software development can be also used, especially in institutions where a lot of research work is done and where numerical tools need to be used with every single research idea and every single research project. Writing computer programs is not easy. It is as much as an art as it is a science. And here is a place where students should be given freedom to explore their creativity and take their creativity and construct something that they have full control over. And the days of using paper and pencil and brain alone to come up with a final solution to the problem those days are gone. Obviously, you have to use your brain and you have to use your paper and pencil to come up with plans, but those plans in the final form need to be in the form of some numerical algorithm that is implemented in the form of a computer program. And using object-oriented approaches in the context of numerical analysis is a very fine way of coming up with very impressive numerical tools that can be used for solving a variety of engineering problems. So with that, I'm going to conclude my talk, and I'm going to open it up for questions. So if you have any questions, please send it to Sridhar, and Sridhar will then communicate with me.
Attendees can send us questions through the chat window.
I'm sure there are people who have questions. I'm hoping that you know exactly how to communicate to Sridhar so that he can then give me a few of those questions. Sridhar, I'm assuming in the past people have asked questions. Is that correct?
Yes, quite unusual. I have not received any questions yet.
Okay. Maybe it's too early in the morning.
No, we'll give them 2 more minutes.
Okay, that's fine.
Dr. B.B. Srivastava, supervisor of doctoral program in Udaipur, says we all like this very much. Many thanks for giving a very clear presentation.
Thank you very much. I'm hoping that there are courses in your undergraduate and graduate program where students are exposed to some form of numerical analysis followed by computer programming. Without that, it's going to be very difficult to do any research work, whether you're doing experimental work or analytical work. It's going to be very difficult to do any work because I do a fair amount of experimental work, and without developing my software to do data analysis of the experimental results, it would be very impossible for me to make sense of the experimental results and then use that in my analytical / numerical modeling work. Maybe Sridhar, if there are no questions, maybe they can formulate the questions and email them to me.
Yes.
Okay, so my email address is s.rajan@asu.edu.
Thank you, Dr. Rajan. In case they have, they need the email address, I can give them to me. They can also email me.
Okay. Okay. So thank you very much for listening. And as I said, if you have any questions, feel free to email me.
Thank
Have
you,
a
sir.
good day.
Thank
Bye.
you.